What up nerds, my name's Ryan. I did my HSC in 2019 and in this video I'm going to go through hard HSC projectile motion questions. Now, if you'd like to see my video on easy and medium questions as well as the theory of projectile motion, click the link in the top right now. Alright, on to the first question. A ball initially at rest in position P travels along a frictionless track to the point Q and then falls to strike the floor below. At the instant the ball leaves the track at Q, it has an initial velocity of 1.5 meters per second at an angle of 50 degrees to the horizontal. And this question is broken into two parts. So part A, calculate the difference in height between P and Q. And part B, the ball takes 0.5 seconds to reach the floor after leaving the track at Q. Calculate the height of Q above the floor. All right, so a lot of these questions are centrally focused on the difference in height between points P and Q, the difference in the vertical height between points P and Q. The first thing to do whenever you get a convoluted question like this is obviously to label the diagram that you're given with all the information, so you don't have to keep referencing all the text. You can just look at the diagram. All right, so a ball initially at rest in position P. So here I'll label the initial velocity as V subscript I, as 0 meters per second, travels along a frictionless track to point Q and then falls to strike the floor below. So I'll draw a little projectile path here, striking the floor. At the instant the ball leaves the track at Q, it has a velocity of 1.5 meters per second at an angle of 50 degrees to the horizontal. So what that means is that we have our horizontal here and our ball is launched 50 degrees to the horizontal here. Now obviously it's not going to be going up like this 50 degrees to the horizontal, 50 degrees above the horizontal, because that just doesn't make physical sense with the track that it's on, right? So it's going to go 50 degrees below the horizontal here. And as I mentioned, a central focus of the parts A and B is about the change in height between the points P and the points Q. So right here I do a little delta H, and then I just remind myself that that is equal to HF minus HI. And also over here where the projectile is at position Q, label this as V subscript F is equal to 1.5 meters per second. Part A again asks, calculate the difference in height between P and Q. So the question is asking us for this delta H term here, the change in height between the ball at point P and the ball at point Q. The easiest way to answer this question is to consider the total energy of the ball when it is at point P and the total energy of the ball at the point Q. And so I'll write that here. I'll say initial total energy. Initial total energy. We know from conservation of energy that the total initial energy and the total final energy is equal. So the initial total energy is equal to the final total energy. The final total energy. And now we have to think about, well, what constitutes the total energy of the ball? What do we mean when we say total energy? Well, we mean the sum of its gravitational potential energy due to its height above a particular reference point and its kinetic energy, right? So gravitational potential energy we know is given by mgh, and kinetic energy is given by half mv squared. And to be a little more specific, I'd put the subscript I on this h and the subscript I on this V, just to remind ourselves that the terms on the left of the equal sign are dealing with the initial conditions of the ball at the point P. On the right-hand side of the equation, we have the same thing. We have the gravitational potential energy, except this time we'll have the subscript F, and the kinetic energy at the final position, so half mv squared with the subscript F again. So firstly, there's a way that we can simplify this equation a little bit, and that is by subbing in the initial velocity of the ball. If we sub in the initial velocity of the ball Vi, which we know is 0, that makes this entire term disappear. And then we don't have to worry about it, right? This entire term disappears. And that just makes it a little bit easier for us to consider the rest of the term. And now what I'm going to do is rewrite the equation mghi, except I'm going to take this mghf term to the other side of the equation. So this is going to be mghi minus mghf, and then with the remaining half mvf squared. The next thing we're going to do to simplify this equation is cancel out the m's, right? Cancel out the mass terms. If we divide the left-hand side by m, this m will disappear and this m will disappear, And if we divide the right-hand side by m, this m will disappear as well. The other thing I'm going to do is divide both sides by this g term here. So if we divide the left-hand side by g, this g will cancel out and this g will cancel out, and we'll be left with a divided by g term on the other side. So if we rewrite this equation, we'll have hi, the initial height, minus the final height is equal to half multiplied by the final velocity squared divided by g, divided by gravity. Now what I'm going to do is take the negative of both sides. So I'm going to multiply both sides by -1. That will leave us with the final height minus the initial height is equal to -1/2 multiplied by the final velocity squared divided by g. And now if you notice on the left-hand side, we have the final height minus the initial height. And that's the same as what we wrote up here for the change in height between the points P and Q, right? Delta H is equal to the final height minus the initial height. So we can replace the left-hand side here with just a delta H. So the change in height, which is the entire point of this question. What's the difference in height between these two terms? And then we can substitute our value for the final velocity of the ball. So in this case, that is 1.5 meters per second squared. So we can substitute this here with 1.5. And similarly, we can do the same thing for G. We know is 9.8. And then if we put all of that into a calculator, -1/2 multiplied by 1.5 squared divided by 9.8, we'll be left with -0.114795 blah, 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 blah meters, right? And the reason it gave us a negative value is because we're really finding the displacement of Q from P, right? And Q is lower down than P, and so we're getting a negative value because we have fallen down, right? We've fallen down by 0.1 whatever meters. And so to really finish off this question, you do a little statement, or I do a little statement saying, therefore, the difference in height between points P and Q, or actually you don't really need that, just the difference in height is 0.11 meters to 2 decimal places. And then, really important point, underline the final numeric answer. Because the way the marker is going to be viewing this, now I've never been a HSC marker obviously, but like what I imagine there, because I think they get paid like per paper or something, they get paid per number of questions they do. So what I would be doing in this situation is just, oh yep, question 30A, 0.11 tick, move on, right? So that's the important point of underlying it. You want to make it as easy as possible for them to see what you've written, see what the final answer is, and then just go, yep, 3 out of 3, next thing, right? They're only going to really look at your work in detail if you've screwed something up. So, yeah, anyway, overall, yep, so in conclusion, underline. Okay, part B. The ball takes t equals 0.5 seconds to reach the floor after leaving the track at Q. Calculate the height Q above the floor. So this time, and I'll just clean this diagram up a little bit. This time we are being asked for the difference in height between the point Q and the floor, right? This is the difference in height we're looking for. Calculate the height of Q above the floor. I'll give it a little Q subscript. So we're going to be viewing this as a pretty standard projectile motion question, right? You've just got some ball that's been launched at 50 degrees below this is a pretty crude drawing, but 50 degrees below the horizontal, and you've been given the magnitude of that velocity, and now you have to use that information to find the displacement from its initial position to some point, the floor in this case, right? So you're basically just going to consider this as a pretty standard projectile motion question. You've got the horizontal that you're considering, you've got a ball which has been launched at an angle to that horizontal, in this case below. You've been given the magnitude of the velocity that it's been launched at, and you need to find out what is the displacement. What is the displacement in the y component of this projectile? So what I would do for all questions of this nature is start with the initial velocity triangle, similar to the one that I drew above. And I'm just going to draw this crudely to show you how I would do it in an exam, also because I'm lazy. So this would be ux and this would be uy. And because you're considering the displacement in the y component, this ux is probably not going to be particularly useful. So we're going to focus on this uy. And we have enough information to find uy, right? We need to think about the 50 degrees and the 1.5 meters per second. What is the relationship of that data to the uy? And in this case, the 50 degrees is opposite the uy, and the 1.5 is the hypotenuse of this initial velocity triangle. And so we have sine of 50 degrees is equal to uy divided by 1.5. And if we rearrange that, you'll obviously get 1.5 multiplied by sine 50. So that's one piece of information that we know, right? uy is equal to 1.5 sine 50. The other things that we know that are relevant is t equals 0.5 seconds. So that's the time of flight. That's what's going to tell the equations that we're going to use how far did it fall, right? Because this initial velocity doesn't tell anything to the equations about how far the ball fell, and neither does this other piece of information, which is the acceleration in the y component is negative 9.8 meters per second squared. This t equals 0.5 seconds is the crucial piece of information in order to find the displacement in the y component. And so now we're going to use our trusty sy equals uyt plus half at squared. Oh, and actually I need to be a little more careful because, okay, this ux is going to the right and this uy is going down. So the value of uy is actually going to be negative. I should have been more careful about this. So the uy is actually negative 1.5 multiplied by sine 50 because it's going in the downwards direction. Whew, okay, so sy is equal to, and we're just going to sub in these values now, right? So sy is equal to negative 1.5 multiplied by sine of 50 degrees, all multiplied by 0.5 for the time, plus half of negative 9.8 multiplied by 0.5 squared. And then from here, it's pretty simple. You just put these values into your calculator. Negative 1.5 multiplied by sine 50 multiplied by 0.5 plus half multiplied by negative 9.8 multiplied by 0.5 squared, and you'll be left with a value of negative 1.79953 ... meters. And then again write your little concluding statement. Height of Q above floor is 1.8 meters to 2 decimal places. Actually, sorry, 1.80 meters to 2 decimal places. And again, we got a negative here because the displacement was downwards. It was in the downwards direction. So we were finding the position of the floor with respect to the point Q. And the question, though, just asked, calculate the height of Q above the floor. So there's no need for a negative. And so that's why I just left it as a positive here. Positive 1.80 meters to 2 decimal places. And then again, underline 1.8. Underline that so the markers can give you many, many ticks. All right, next question. A spring is used to construct a device to launch a projectile. The force F required to compress the spring is measured as a function of the displacement X by which the spring is compressed. Okay, so all that's saying is we have some spring here. We push it a certain displacement, and it's requiring a force of F, which is related to that displacement. So it's just going to be something like F is equal to Kx, where K is the constant that relates the displacement and the force. So it's just saying that the force is proportional to the displacement of the compressed spring. The potential energy stored in the compressed spring can be calculated from potential energy is equal to half kx squared, where k is the gradient of the force displacement graph shown. So k is the gradient of this force displacement graph shown. So let's find that k value. Let's find the gradient of this line here. So k is going to be equal to the rise over the run of this line of best fit. And the way that we can find the rise over the run is by taking or considering 2 points that exist on the line. So I'm going to consider this point up here, which looks to be 24, and it corresponds with this 0.08 here. So we're going to do 24 minus 0 divided by 0.08 minus 0. So this is obviously just equal to 24 divided by 0.08, which if you put in a calculator, which is equal to 300, and you might want to say newtons per meter. So that's a very critical value that we're going to be using in this question. So part A projectile of mass 0.04 kilograms is launched using this device being this thing here, with the spring compressed by 0.08 meters. Calculate the launch velocity. Okay, so what is it asking us? Well, so it's saying that we initially have a compressed spring, as we can see in this graph here, and a projectile. And once this compressed spring has been released, what it's going to do is extend out to its uncompressed length, and the ball is going to be pushed a certain distance. It's going to have a certain velocity that it then flies away from the device here. And it's asking us to find, okay, well, what is the velocity of the ball as it leaves the device? Now, you might be tempted to consider the velocity of the ball as it leaves the device as the initial velocity. I think it's better to think about it as the final velocity. So we have some v subscript f. And the reason I say we should consider it as the final velocity is because the initial velocity of the ball can be considered here. And we know what that is because it's just stationary. It's just equal to 0. The initial velocity of the ball is equal to 0 because the spring is being compressed and it hasn't been released yet. So that's one piece of information that we already know. We're also given a value for the displacement x here, just like this x here that's telling us the difference between the compressed length of the spring and the uncompressed length. We are told that with the spring compressed by 0.08 meters, so that's an x that we're given. That's a displacement that we're given. And here, of course, we're given the mass of the actual object. So how do we calculate the launch velocity? Well, one piece of information that we're given is that potential energy is equal to half kx squared. So first thing I do immediately is write that down. Potential energy is equal to half kx squared. We found x as 300, so we can write this as half multiplied by 300 multiplied by our value for displacement, which is 0.08 squared. And if you put that in the calculator, 0.5 multiplied by 300 multiplied by 0.08 squared, you will get 0.96 joules, because this is a value for potential energy. Okay, so we have the potential energy of this like spring ball system thing, right? We know the initial energy. So this is the potential energy initially when the spring has been compressed. So then consider what would be the potential energy of the spring when it's uncompressed. Well, if it's uncompressed, then the displacement x here is equal to 0 because there's no difference between the uncompressed length and the uncompressed length. And then so we'd have a final potential energy, again equal to half kx squared. And maybe you can consider the x as x initial and x final if you wanted to. And then this would be equal to half multiplied by, again, 300 multiplied by 0 squared. Because there is no displacement, because the spring is returned to its uncompressed length. And so this would just be 0. But in order to get a value for velocity, there's another concept that we need to consider. We can utilize the information that we have about the potential energy, but we also need to consider kinetic energy. Now, from conservation of energy, we know that the total energy initially is equal to the total energy finally. And in this case, our energy is made up of the potential energy of the spring and the kinetic energy, right? So we have half kx initial squared, that's the potential energy initially, plus half mvi squared, which is the kinetic energy initially, is equal to the same thing on the right except with subscripts of f. So half kx f squared, which is the potential energy finally, plus half mvf squared. And this vf, the final velocity, is exactly what we're looking for. That's the launch velocity. That's this velocity here. which is the entire point of the question. And so all we need is values for everything else in this equation, or make a bunch of other things disappear, in order to rearrange all of this for VF. And that's exactly what we're going to do. And so half kxi squared we know is 0.96. So 0.96 plus half mvi squared. What's the velocity of the ball initially? Well, it's 0, because the spring isn't pushing it with any force to launch it, right? It's just stationary there. And so vi is going to be 0. So this is going to be half m, which is 0.04 multiplied by 0 squared, is equal to half kxf squared. What's the displacement of the spring after it returns to its uncompressed state? Well, that's just 0, right? This x value here for an uncompressed spring is just 0. So if we sub in 0 to that xf, we get half multiplied by 300 multiplied by 0 squared. And now the final kinetic energy is plus half m, which is 0.04, which we were given in the question, multiplied by the thing we are trying to find squared. And remember, this VF is the thing we are trying to find. And so the kinetic energy term on the initial side of the equation is just disappears because we've got a 0 multiplying everything. So 0.96 is equal to. Similar thing here, the potential energy of the final position on the right-hand side of the equation also disappears because we've got a 0 multiplying everything, so that's a 0 here, and maybe I'll write the zeros in just to be clear. And then here we've got plus 0.02 multiplied by VF squared. Now I'm going to flip these equations to make it a little bit neater, and I'm also going to divide both sides by 0.02. So 0.96 divided by 0.02 is equal to 48. And then if you take the square root of both sides of this equation, you will get VF is equal to 6.92820 ... meters per second. Therefore, launch velocity, it's always good to use the same wording that the question uses, right? Calculate the launch velocity. Therefore, launch velocity is 6.93 meters per second. Underline that to 2 decimal places. Really underline that, make it clear. A projectile is fired horizontally from a platform. All right, so let's just draw that quickly. We have a projectile here. It's been fired. Let's make that horizontal. It's been fired horizontally from a platform with an initial velocity of u equals (meters per second. It travels in a standard parabolic path and lands in this position marked with an x down here. Its displacement in the x component of its motion from the base of the platform, as measured from the base of the platform, is this distance here, the distance traveled from the base of the platform. And its displacement in the y component from its initial position is going to be, in magnitude at least, equal to the height of the platform here. Now, why do I say in magnitude? Well, the displacement is going to be negative because the projectile is starting at some height and then falling down. And so we're going to have some negative value for sy. Let's just say -5 meters. The height of this platform is going to be equal to the magnitude of the displacement in the y component. In this case, it would be the magnitude of -5, which is just 5 meters. So be careful with the difference between displacement and height because it's maybe critical for this question. Measurements of the distance traveled by the projectile from the base of the platform, and maybe I will highlight that in the same light blue color. Okay, the distance traveled from the base of the platform are made for a range of initial velocities. Okay, so when the projectile is fired with an initial velocity of 1.4, we are told that the distance traveled from the base of the platform will be 1. When it's 2.3, it'll be 1.7, etc. So in this first column, we have an independent variable. Independent variable. That is something that is being varied by the experimenter. And in the second column, we have the dependent variable. This is something that is dependent on the value of the independent variable. So obviously the distance traveled from the base of the platform is going to be dependent on the magnitude of the velocity that the projectile has been launched. And that's very, very intuitive. If you launch it with a small velocity, it's going to go like this. If you launch it with a larger velocity, it's going to go further, right? So that's just something to consider. If you want to watch a video that goes into more detail about independent and dependent variables, you can watch the video I did on projectile motion investigations by clicking the link in the top right now. Okay, graph the data on the grid provided and draw the line of best fit. Okay, so the first step is to just look at all these values and plot them on this graph here. And as we should, we have initial velocity, the independent variable on the x-axis, and distance traveled from the base of the platform on the y-axis. So at initial velocity 1.4, the distance traveled is said to be 1. So at 1.4, which would be here, 1.4, the distance traveled is said to be 1, which is this line up here, and we mark that with a little x. Okay, initial velocity of the projectile, 2.3, distance traveled 1.7. So 2.3 and 1.7. 2.3 would be here, 2.3, and 1.7 would be 5, 6, 7. 1.7 would be here. So 2.3 lining up with 1.7 there. At 3.1, the distance traveled is 2.2. So at 3.1, which would be here, the distance traveled is 2.2, which would be here. At 3.9, it's 2.3, so 3.9 would be here. 2.3, oh, it seems like a bit of an outlier. 2.3, which would be this point here. Yeah, that's definitely an outlier. So maybe just make a little note to yourself. 4.2 is 3, so 4.2 here is 3. So now we've graphed the data. You might want to double check it. I'm pretty confident that that is correct. Draw the line of best fit through this data. So remembering that the fourth data point is an outlier, we're just going to ignore that when drawing a line of best fit. So the line of best fit is going to look something like this. It's going to line up at 0, because if we launch it with a velocity of 0, it's not going to travel anywhere. And then say about there. Part B, calculate the height of the platform. And so, I was talking about how there is a relationship that exists between the value for the height and the value for the displacement in the y component. So in order to find the height, we should find the displacement in the y component. And you can consider the kinematic equation Sy equals uyt plus half ayt squared. So in order to find this Sy, we need information about the initial velocity, we need information about the time, and we already know what ay is if we're just assuming that this is on Earth. But do we have information about uy? Yes, we do, because the initial velocity in the y component was 0 because it's being launched horizontally. So I'll just write some of the data, some of the relevant data that we have first. So uy is equal to 0. For that equation, Sy equals uyt plus half ayt squared. We also know that ay is equal to negative 9.8. We don't yet have information about t, so that is something that we need to find. What information do we have, though? Well, we have information about the displacement in the x component of this projectile's motion. And so if we consider the same equation, but for the x component, Sx is equal to ux times t. If we rearrange this equation to make t the subject, we get t is equal to Sx divided by ux. And we actually have information about Sx divided by ux. That's just the gradient of this line here. On the y-axis, we have Sx, and on the x-axis, we have ux. And so the gradient of this line of best fit is going to be equal to t, which is equal to Sx divided by ux. And so if we consider 2 points on this graph, let's consider 2.5 and 3.5. Oh, I should say it the other way around, really. 3.5 and 2.5. So this 3.5 here and this 2.5 here gives us this nice, neat little point here. And we'll also consider the point 0, 0. So 2.5 minus 0, which is the rise, divided by the run, which is 3.5 minus 0, is just equal to 2.5 divided by 3.5, which is equal to 5/7 seconds. Remember, because this is equivalent to time. 5/7 seconds. So t is equal to 5/7 seconds. Now we can use this information about the time that it took for the projectile to move from its initial position to its final position. We can use that information about time and plug it in to the sy equals uyt plus half at squared equation in order to find what we're actually looking for, the displacement in the y component, so that we can find the height of the platform. And so sy is equal to uy, which is 0, multiplied by t, which doesn't matter because it's being multiplied by 0, plus half of negative 9.8 multiplied by 5 divided by 7 squared, which is equal to, if you put that expression into the calculator, you get negative 2.5 meters. So that's, again, the displacement is negative because the ball has fallen down, it has traveled down, but the question hasn't actually asked us for the displacement in the y component, it's asked us for the height, and the height is just going to be the absolute value of this. So therefore, height of platform is 2.5 meters, and underline that. All right, next question. The set of data was obtained from a motion investigation to determine the acceleration. So we're not given the acceleration, we're not assuming the acceleration, we're determining the acceleration, we're trying to find a value for the acceleration. To determine the acceleration due to the gravity on a planet other than Earth. And we're given this set of data here. In the first column we are given time, and in the second column we are given vertical velocities which correspond to each time value. Plot the data from the table. So plot the data from the table and then calculate the acceleration. Okay, so we're just going to plot this data real quick. At time 0.6, at time 0.6, we have a vertical velocity of 0.02. So 0.06 corresponds, okay, let's figure out what this scale is first actually. So this would be 0.2, this would be 0.1, this would be 0.05, and this would be 0.15, and this would be 0.25. And be careful there, because you could have easily confused yourself. You could have written a 1 there and then written a 1.5. And when I say could have, I don't mean that it's a valid answer. I just mean that you could have fallen into that trap. Okay, time 0.6 and vertical velocity 0.02. So 0.6 is here and 0.02 is here. So 0.02 is here. And so then we mark the point here. Time 1, 0.09 for the vertical velocity. So at time 1 we have 0.09 for the vertical velocity, which would be this point here. Time 1.2 is 0.12. So time 1.2 is 0.12. Time 1.4 is 0.17. So time 1.4 is 0.17. Time 1.8 is 0.23. So time 1.8 is 0.23. And now we are going to draw a line of best fit as we would usually, which is going to look something like this. And then we are going to use that information from this graph to calculate the acceleration. And so we should remind ourselves of the fundamental definition of acceleration, which is that acceleration is equal to the change in velocity divided by the change in time. And on the y-axis, we have a vertical velocity, and on the x-axis, we have time. And if we're finding the acceleration in the y component, all that matters is the change in velocity in the y component. And right here we have, and like obviously we're trying to find a value for the acceleration due to gravity, and so we're only going to be considering ay. We're not going to be considering any ax as standard for HSC physics. So here we're just going to find the rise over run of this line of best fit. So we need to select 2 points with clear values. And so I would say that 0.235 is 1 point here, and that corresponds to 1.8. And 0.02 corresponds with this 0.6. And so using those 2 points, we're just going to find the rise over run. So that's 0.235 minus 0.02 divided by 1.80 minus 0.60. Put that into a calculator and you will get 0.17 0.916 blah 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 meters per second squared. And so therefore we can say that, and maybe I should have actually done all this working down here. Ooh, let's try and make this fit. Okay, roughly. Anyway, you know what the working is anyway. Therefore the acceleration due to gravity has a magnitude of 0.18 meters per second squared to 2 decimal places. Underline that value and go to the next question. Yes, the dreaded bird question. Okay, if I remember correctly, I would typically use, when I was practicing for my HSC, I would use solving two simultaneous equations to answer this question. So if you don't know how to solve simultaneous equations, I'd recommend you look that up or just skip this question. If you're a bit shaky, then I'll try and go slow enough that you can understand. A toy bird is launched at 60 degrees to the horizontal from a point 45 meters away from the base of the cliff. So this bird is launched 45 degrees to the horizontal at a point 45 meters away from the base of the cliff. Calculate the magnitude of the required launch velocity, such that the toy bird strikes the base of the wooden building, here at the top of the cliff, 34 meters above the launch height. So our displacement in the y component is equal to this 34 meters. The displacement in the x component is equal to this 45 meters. The initial velocity is the thing that we are trying to find. We're still assuming that the acceleration due to gravity is negative 9.8 meters per second squared. And let's just consider ux here and uy here. We can say that ux is equal to u cos 45. If we just use our standard trigonometry, you can find that. Uy is equal to u sine 45 because its relation to the angle is opposite. What else do we know about the x component? Well, we know that sx is equal to 45 meters because once the bird travels from its initial position to its final position, the displacement of the final position with respect to the initial position is going to be 45 meters. And similarly, in the y component, the displacement of the bird from the final position with respect to the initial position in the y component is going to be 34 meters up. So sy is equal to 34 meters. We know that the acceleration in the x component is 0 meters per second, and we know that the acceleration in the y component, or we can assume that the acceleration in the y component is negative 9.8 meters per second squared. And we don't know anything about the time yet. So let's use our trusty sx equals uxt, and then you can write the plus half at squared. A is 0, so it cancels out the plus half at squared. And we can say that 45 is equal to u. Remember, u is what we're trying to find, right? So we're trying to find the initial launch velocity. So we have 45 equals u cos 40 multiplied by t. And for the y component, we can use, again, our trusty sy equals uyt plus half at squared, ayt squared. Sy is 34 equal to u sine 45 multiplied by t plus half of negative 9.8 t squared. And so you can see what we have here is two equations, this being the first equation, this being the second equation, which have two unknown variables, u being the one that we're interested in and t being another variable that we don't know. And here we have the u and the t's here. And if you have two unknowns and two equations, two different equations, you can use a technique called solving simultaneously in order to find either of those variables. To make this a little bit easier, I'm going to rearrange the first equation for t. So t is equal to 45 divided by u multiplied by cos 45. And actually, it's not 45 degrees, is it? I just realized that. It's 60 degrees, sorry. So all of the things that had degrees in them need to change. So that's 60 degrees. That's 60 degrees. I'll just change these quickly. Okay, sorry, I didn't see that. They're all 60 degrees now. And cos of 60 degrees, if you put in the calculator, gives you a half. And we have a half in the denominator of this expression here. So that's going to be equivalent to multiplying the whole thing by 2. And so t we have as 90 divided by u. On the other side here, we have 34 is equal to u sine 60, and sine 60 is equal to root 3 over 2. So we have root 3 ut divided by 2 plus, actually not plus, we have negative 4.9 t squared. And so I'm going to call this equation 1 and this equation 2. And what I'm going to do is substitute equation 1 in its entirety into equation 2 and then rearrange for u. Because what's going to happen is the t's in the second equation are going to be expressed in terms of a u. So we're not going to have any t variables left, and u is the variable that we are trying to find. So solving simultaneously will produce 34, and you might want to say like sub 1 into 2. 34 is equal to root 3u divided by 2 multiplied by t, which we are substituting as 90 divided by u, minus 4.9 multiplied by t squared, which we are substituting as 90 divided by u, all squared. And then we can simplify this equation by saying that this u up here cancels out with this u down here. The 2 in the denominator here will make this 90 into a 45. So 45 root 3 minus 4.9 multiplied by 90 squared divided by u squared. And that's just distributing this squared term to the 90 and the u. And then we rearrange this equation to solve for u. So take this entire 4.9 multiplied by 90 squared divided by u squared to the other side, and you'll get 4.9 multiplied by 90 squared divided by u squared is equal to 45 root 3 minus 34. Multiply both sides by u squared, and you'll end up with 4.9 multiplied by 90 squared equals 45 root 3 minus 34 multiplied by u squared. Divide both sides by this term here, and you'll end up with u squared is equal to, and I've just flipped the order of the expressions, it doesn't change anything other than the visual presentation. If you divide both sides by the term in this brackets here, we'll get 45 root 3 minus 34 in the denominator and 4.9 multiplied by 90 squared in the numerator. And then we just take the square root of both sides, which will leave us with this expression here. And if we put that into the calculator, we get 30.053788 blah 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 meters per second. Therefore, launch velocity is 30 meters per second. Underline that, 0 decimal places. Okay, next question. An astronaut on the moon, so acceleration is not going to be the same as what we usually use, throws a stone from the top of a cliff. The stone hits the ground below at 21 seconds later. 21 seconds later. The acceleration due to gravity on the moon is 1.6 meters per second squared. So we know that this astronaut throws the stone with some initial velocity u meters per second. It travels a parabolic path, lands down here. The time taken, the flight time, is 21 seconds. And the acceleration in the y component is negative 1.6 meters per second squared. And I'll just move that down over here. And we should just notate the fact that we are also given the displacement in the x component as 300 meters, and the displacement in the y component is going to be negative 150 meters. The displacement in the y component is going to be negative 150 meters. Calculate the horizontal component of the stone's initial velocity. Show you're working. Okay, we can break this initial velocity vector down into its x component, ux, and its y component, uy. And then if we write down everything that we know about the horizontal component, we know that sx is equal to 300 meters. We know that ux is going to be equal to u cos of some angle that we're given. We're not necessarily going to use that, but we can write it anyway. Su Vx we don't know, Ax we know is 0, and T we know is 21 seconds. So we'll just use the standard Sx equals Ux plus half At squared. Ax is 0, so it's just Sx equals Ux multiplied by T. Sx equals 300 equal to Ux, and we could substitute in that U cos theta, but because we're just finding ux, we don't need to, right? If we were finding u or theta, then perhaps we need to sub it in, but not in this question because we're just being asked to find the initial velocity in the horizontal component. Okay, and then multiplied by the time, 21 seconds. Divide both sides by 21 and you'll get ux is equal to 300 divided by 21, which is equal to 14.29 meters per second when written to 2 decimal places. Underline that. Part B, calculate the vertical component of the stone's initial velocity show you're working. So this time we're considering the vertical component. We know that Sy is equal to negative 150 meters. Uy, we don't really need to write down because that's the thing that we're finding. Vy, we don't know. Ay, we know is negative 1.6. So be careful not to forget that we're not on Earth anymore. And then T is equal to, again, 21 seconds. And now we use Sy equals Uy T plus half Ay T squared. This is basically the same exact question, except now we have an acceleration to deal with. So negative 150 is equal to Uy, which is the thing we're trying to find, multiplied by T, which is 21, plus half of negative 1.6 multiplied by T squared, which is 21 squared. Take all this stuff to the other side and you end up with 21 Uy is equal to half of 1.6 multiplied by 21 squared minus 150. Divide both sides by 21 and you'll end up with 0.5 multiplied by 1.6 multiplied by 21 squared minus 150. All of that divided by 21 is going to give you 9.66 meters per second when written to 2 decimal places. Underline that. Part C, on the diagram, sketch the path that the stone would follow if the acceleration due to gravity was higher. So if the acceleration due to gravity was more powerful, the initial velocity is the same. Okay, well, that's pretty easy. You just, you know what, like, you can think about what would happen if there was no acceleration. Well, it would just go off in that direction there. It'd just keep flying off to infinity. And what would happen if the acceleration was extremely, extremely high? Well, it just kind of falls straight down. Not exactly in that path, but it'd be like, you know, it'd fall really far down. And so if the acceleration is higher, it's going to, you know, quote unquote, pull the board down faster. And so the path of the projectile is still going to be parabolic. It's just going to not travel as far or reach a maximum height, which is as high. All right, and that is it for projectile motion. The next video is going to be on HSC circular motion theory, and you can access the Module 5 Advanced Mechanics playlist at this second link down here. Good luck, and I'll see you in the next video.